everyone. We are going to go through an example now of doing a confidence interval for the slope of a true regression line. So in life, we're not always getting all of the data from the entire population. We're getting from a sample. So the line of best fit that we get is just a sample prediction. So what is the true slope, right? We have an estimate for the slope. We want to find the true one. So let's read our context. For their second semester project, 2 AP Statistics students decided to investigate the effect of sugar on the life of cut flowers. They went to the local grocery store and randomly selected 12 carnations. All of the carnations seemed equally healthy when they were selected. When the students got home, they prepared 12 identical vases with exactly the same amount of water in each vase. They put 1 tablespoon of sugar in 3 vases, 2 tablespoons of sugar in 3 vases, and 3 tablespoons of sugar in 3 vases. In the remaining 3 vases, they put no sugar. After the vases were prepared and placed in the same location, the students randomly assigned 1 flower to each vase and observed how many hours each flower continued to look fresh. Here are the data and computer output. So this right here is my computer output. So before I even get to like my confidence interval stuff, let's make sure we know how to read the computer output and figure out things from it. This number right here, the 181.2, that is your y-intercept. Okay, that's your y-intercept. The number beneath that, the 15.2, that number is going to be your slope. Okay. Other important numbers, this 1.943, that's going to be the standard error of your slope. So your standard error of your slope, right, our lowercase b slope, not our true slope. This capital S down here, that's going to be the standard deviation of your x values. So this is standard deviation of your x values. Obviously we have r squared is here. From your slope and your y-intercept, we have our prediction equation, right? Y hat would equal 181.2 plus 15.2 x. Okay. So that's how we read our computer output. Over here we have our actual data. Now, this information came from an experiment. So keep that in mind when we do our independent condition because we won't need to check the 10% condition. Alright, so we want to construct and interpret a 99% confidence interval for the slope of the true regression line. We're still going through our 5-step process. We still have to come up with a state, we still have to say a plan, we still have to do some math, and we have to come to a conclusion. So, let's start with state. Okay. What do we want to do here? Well, we want to estimate the slope, and not lowercase slope b, but the Greek slope beta, of the true regression line relating the hours of freshness y to the amount of sugar x. Usually in our state we have to define our parameters. When you're talking about slope, since it's from a regression line, you're going to have an x variable and a y variable. So we're saying how they relate, so it's relating something to something. So in this case it's relating the hours of freshness, which was in our y column, to the amount of sugar, which was in our x column. And as always, state the level that they gave you. Okay, so for our plan, we need a plan. If our conditions are met, we're going to use a t-interval for the slope in order to estimate beta. This is where it became important to not just say, oh, I'm going to use a t-interval, but I want to use t-interval for slope versus t-interval for means, which was something we did in the previous chapters. So if our conditions are met, we will use a t-interval for the slope to estimate beta. For our conditions, we now have 5 conditions that we need to verify using the acronym LINER: linear, independent, normal, equal variance, and random. So, first one, linear. When you're checking your linear condition, you need to look at the scatter plot and or the residual plot. I kind of like looking at both of them so you can mention both of them. So what we need to do now, get your calculator out, put your data in list 1 and list 2, and we're going to make a scatter plot and a residual plot. Now that we have our data in our lists, right, X in list 1, Y in list 2, I'm going to go ahead and create the scatter plot for it. So if you don't remember how, go up to your Y equals, turn your plot on. If you hit second Y equals, we're going to go in here and make sure we hit scatter plot, which is the very first one. X's are in list 1, Y's are in list 2. When you go to zoom, this is, oops, not that. Quit out of that first. Go to zoom, and then we always pick option 9, zoom stat. And then here is my scatter plot. How beautiful. This scatter plot clearly shows a linear pattern, so that's what I'm going to write for my condition. If this were a test, you would have to, if they don't give you this, you would have to make a scatter plot so you can reference it. Don't just be like, there's a random scatter plot that I did and it's linear. No, you have to draw it out. Most of the time that I've seen, either on tests that I give you or on the AP test, they provide you with the scatter plot, so you just have to reference it and say, hey, here's the scatter plot, look, it's linear, we're good to go. I also want to do the residual graph, just so you can see what that interpretation would look like, because if they didn't give you the scatter plot and they only gave you the residual plot, you'd have to talk about that. So to get your residuals, you have to go back to your lists. I don't think I stored my equation, so let's go ahead and do that. If I go to stat calc number 8, it's going to give me my things. In order to store it, I have to go to vars, yvars, function, and y1. I did this in the last video, so if you're like, this is too fast, either go watch that one or redo this one. All this is doing is it's giving me the line of best fit, which we already knew from our computer output. So I actually guess I didn't need to do that because it gave me the computer output. So I could have put my data there. So then when you would go to graph it, if you wanted to see, there's that line of best fit with the data. But the reason we did this is because when we do our lists, we want to calculate the residuals. Residuals come from your actual Y values, which are in list 2, minus your predicted ones, which are in not list 1, but you're going to plug that in. So I'm blanking. What do I put first? Y1 goes first. And then, yeah, that's it. And we put L1 there. So what this is doing is it's plugging in X for that, depending on the different X values. And those are my residuals. There we go. So then to make your residual, you go ahead and you go to your stat plot. We're now comparing L1 and L3. I don't need my equation on anymore, so I'm just gonna turn that guy off. And so here's my residual plot. What we can see is that it shows a random scatter of points about this residual equals 0 line. So this is also part of the linear condition. Alright? It's short. So, because this came from an experiment, we don't need to check the 10% condition. So when it comes to independent, as long as we're saying that, you know, all the flowers were in different phases, so knowing the hours of freshness for one shouldn't provide additional information about the other flowers, that's good enough for our independent. So just saying, you know, one thing is independent of the other, throwing in some context, you're good there. So now that we've done independent, we have to do normal. Couple ways to do normal. You can either do a histogram or a stem plot of the residuals, or you could make a normal probability plot. Either way, you would just need to make sure that there's no outliers or skew in the histogram, or your normal probability plot should look roughly linear. And you're doing this with the residuals. So what I'm going to do is I'm going to clear it of that. My equation's already turned off, so I'm going to make a histogram. And that is this graph right here. And I'm only doing it for my residuals, which are currently in list 3. So I go out of there. And look how beautiful my histogram. Doesn't show me any outliers. Doesn't look like there's any skew. So I'm good for normal. So we're almost through our conditions. And then we just have to do the do and conclude. Next condition is a new one for us. It's called equal variance. Equal variance. You're going to be looking at your residual plot here, which we've already seen. Okay. So if we looked at our residual plot, we wanted to make sure that it was basically evenly balanced above and below. Kind of like a nice random pattern, not a clear pattern as far as how they're distributed. So what we can say, so in reference to our residual plot, the variability of the residuals is not constant, but there's no systematic pattern. For instance, like increasing variability as x increases. You don't need to write in this extra part, like I'm just doing this now so you kind of are aware of what I'm talking about. The last condition is random, probably the easiest one. Flowers were randomly assigned to the treatments, so that takes care of that condition. Our flowers were randomly assigned to treatments as well as the flowers being randomly chosen at the grocery store, so we are fulfilling the random condition all around. Okay, whew, halfway there. We've done our state, we've done our plan. Now we can do and then come to a lovely conclusion. Now, this is new-ish for the do stuff, okay? Because we're using a t interval, we need to have a degrees of freedom. Degrees of freedom for this case is always n minus 2 for slope. N here was like how many coordinates, I guess you would say. So in this case, it is 12 minus 2, so my degrees of freedom is 10. Okay? We would then need to get our t star for this. And I would want to use my calculator. So we can do inverse t. So if it's a 99% confidence interval, I'd want to look up, let's see, half of 99 is 0.01, half of that is 0.005. And then my degrees of freedom is 10. That's going to give me a negative value, but as always, we use the positive of it. So that's what I get from my calculator. All right. Then comes the formula. So you're taking your estimate, which is our b, our slope, add and subtract your critical value, your t star, times that by the standard error of your slope, which the b and the standard of the slope came from your computer output above. So my sample slope was 15.2 plus or minus 3.169 times 1.943. So your lower estimate 9.04, your upper estimate 21.36. And then all that's left to do is to conclude, right? We are 99% confident that the interval from blank to blank captures the slope of the true regression line relating context. Conclusion's pretty much the same as what we're used to. State the level of confidence, say your interval, say what you're actually capturing, so in this case the slope of the true regression line, and then don't forget your context relating whatever your y is to your x. Okay. The next example goes through a hypothesis test for this. Basically the same except writing your hypotheses. You'll figure that out based on what they tell you in the problem for your alternative. And then after that, new way to calculate your test statistic, and then coming to a conclusion as per usual. Okay? Stay tuned.